Okay, so for those that are interested in how the Lagrangian comes to be the tool we use in MaxEnt, I want to give a short video explanation of that to accompany the appendix in the course. We'll use a very simple example here, and you'll see that the Lagrangian just falls out of some basic reasoning. So we'll use a geometric example here. So we have our x and y axis, and we have our function, which here is h of y, which is our entropy, right? This is the thing that we are trying to maximize subject to certain constraints. Now, don't take the shape of everything here very literally. I don't think that entropy looks like that exactly, but this is just for conceptual purposes. So normally, if we were trying to maximize a function, we would take its derivative, set that derivative equal to 0, and then solve for the quantities that we needed once we set it to 0, right? So hopefully you're familiar with that from basic calculus. If not, that's a little bit beyond the scope here, but there's a lot of free resources about how to take derivatives, etc. But the important part is that the maximum, or sometimes the minimum, here we're just going to assume it's the maximum. The maximum occurs at the point, or at least a local maximum occurs at points where the derivative of the function is 0. Okay, or undefined. Sorry for all the caveats. Okay, anyway. What we want to do here is we want to maximize this function, but we don't want to maximize it absolutely. We want to maximize it subject to certain constraints. And here that constraint is being represented by the blue line. Again, don't take the shapes too literally here, but we usually represent these constraints as the expected value of some function of y, and we set that equal to a constant. And often that constant is an estimated value of that function of y from the data or some other means of estimation. And so we can rewrite that top expression as the expected value of g of y minus the estimated value of g of y, or whatever constant, and set that equal to 0. Okay? And so now we're going to try to maximize entropy subject to that constraint, right? And so geometrically, this is the point where the two surfaces touch, and so that's fine, that's cool, that makes a lot of sense visually, but how do we actually find that point, mathematically? Okay, well, that point occurs where the gradients of both the constraint and the function h of y coincide. And so that point is represented there with that purple circle, and you see that they are tangent to one another. Okay, and so we can write the expression that point is where the gradient, that's what that upside down triangle is, it's called a nabla, where the gradient of your function h of y equals, we'll get to this lambda here in a second, but equals the gradient of your constraint. Okay, actually it's when the gradient of the entropy is proportional to the constraint, to the gradient of the constraint, and then this lambda is a little parameter that we estimate to make the gradient of the constraint bigger or smaller so that the two sides are equal. Okay, that's exactly what we're doing when we're solving these MaxEnt problems. Okay, so we can rewrite this, of course, bringing the constraint over, or bringing one side over to the other, and we get this expression. Well, what is this expression? This expression is just the gradient of the Lagrangian, right? So this is how the Lagrangian is representing our constrained maximization problem, right? And so we go through and we solve this or we set this value to 0, either analytically or numerically, and then we go about solving for the parameters. And one of those parameters is going to be the Lagrange multipliers, those lambda values. But through that, and we'll see how, we'll also get expressions for the probability of y.